This is A-Level Computer Science 9618, Paper 3, Chapter 3, Hardware and Virtual Machines. Okay, so in this video we are going to understand about processors, parallel processing, and virtual machines. The type of processors, pipelining registers, interrupt handling architectures. There are 4 types of architectures, and where do we use and why do we use it? What is the examples of parallel computers and virtual machines, the example and benefit and limitations, and then we're going to understand about the Boolean algebra and logic circuits, which they are made for memories, made in memories, and how to make a simple logic using Boolean algebra and Karnaugh maps. Okay, so let's start from here. So here you go. Let's start from CISC and RISC. So the difference between these two is CISC is mainly used in desktop computers, and CISC contains contains a single complex instruction, which then handed over to the hardware, and the hardware do the hardware do all the main stuff. Okay, we can write simple few lines of assembly code, and then we just hand it to the hardware because we depend on mostly on the hardware to do all the complex stuff. Okay, so the hardware should be chosen to suit the high level language development, carry out a given task with as few lines of assembly code as possible. Processor hardware must therefore be capable of handling more complex assembly code instructions. Okay, so writing few code, but you just write a few lines of code, few lines of single complex instruction, and then you just hand it to the hardware to do all the complex stuff. So single complex instruction which need to be converted by the processor into a number of subset instruction to carry out the required operation. So the processor converts a single instruction to a sub instruction. Use the memory unit to allow complex instruction to be carried out. Long execution time for instruction. Make use of multi-cycle instruction used in desktop computers. Okay. Now RISC processor has fewer built-in instruction format, which leads to higher process. It use less complex instruction, which means you are doing more coding, but you're not completely dependent on the hardware because you're doing more coding. Okay, so use of less complex instruction, which is done by breaking up the assembly code instruction into a number of simpler single cycle instructions. Have fewer built-in instruction format, which leads to higher process performance. Optimization of each of these simple instruction is done through use of pipelining. We will discuss what is a pipelining. Simplicity of the instruction allow data to be stored in register and manipulated in them with no resource to memory. The design up here is on the software. Use in portable devices such as tablet, laptop, mobile phones, etc. Okay. Have fewer built-in assembly format, which leads to higher fewer built-in instruction format. There are fewer instruction formats. Okay, so the instruction is not that much complex. So yeah, pipelining. What is pipelining? So it's more like it's a method where you can do a less complex way of improving computer performance, doing much faster. Doing all the things together. Like each instruction is going through instruction fetch, instruction decode, or operand fetch, instruction execute, result, write back. Each instruction is going through all of these 5 stages. So we can just, if you are having 3 instruction, then we can execute all 3 or all of them simultaneously by just merging one. Like for example, in the first stage you just start all of them. In the first stage you start with the first cycle, which you start this first instruction. Then on the second stage, on the second cycle, you start with the B, and then you just put A into here. Okay, so the difference is, if for example you're not using pipelining, then it means that you would have done like this, like A, and then separately B, and then C. But now what you're doing here, that you are doing simultaneously. You are reducing the time effort. You're just trying to make sure it happens so fast. Okay, you're doing simultaneously. Okay, so improve performance like that. So allow several instructions to be processed simultaneously without having to wait for previous instruction to be completed. Okay, fetch, decode, execute cycle can be separated into a number of stages. So these are the stages, and the last part is write the result back to register memory. The construction of the processor must have 5 independent units. This explains the need for a RISC processor to have many register sets. Each processor unit must have access to its own set of registers. Okay. Then we have interrupt in RISC processor. Okay, so interrupt handling, normally that interrupt happens in the CISC is very normal. Like in a computer, you just wanted to print out a piece of paper, so the printer sends an interrupt message, so it's normal in CISC processor. But what happens in RISC processor, and it could be possible chances that the interrupt could happen if during pipelining. Okay, so let's discuss this. So interrupt, the approach where a check for any interrupt is made following the execution of instructions applicable to CISC processor. It's very normal. We have already know what interrupt is. It's normally happening in CISC processor in the computer desktop, but what happens in mobile phones or tablet. Okay, interrupt during the pipeline. There will be 5 instructions in the pipeline when an interrupt occurs. One option is discard all instruction in pipeline except for the last instruction in the write back. In the discarding all of them except the last one. The interrupt handler routine can then be applied to this remaining instruction, and once serviced, the processor can restart with the next instruction sequence. The second option is that the content of the 5 stages can be stored in registers. This allows all current data to be stored, allowing the processor to be restored to its previous status once the interrupt has been serviced. Okay. So the second option is that the content of the 5 stages can be stored in registers. Okay, and then this will allow all current data to be stored and allow the process to be restored to its previous state once the interrupt has been restored service. These are 2 options for handling interrupt during pipeline. Okay, now we are coming to architectures. There are 4 types of architectures. The first one is SISD, which means single instruction, single data stream. Single data stream, single instruction. Execute a single instruction which operate on a single data stream. For example, you have a data stream 5 and the instruction is to multiply by 2, so you will get 10. Then you get the next instruction is to add 2, then you just do 10. It becomes 12. Then you get the next instruction to subtract it by 8, then you just do, and you get 4, like that. Okay, so single instruction operate on a single data stream. So process in a sequential manner, like the same thing I just showed you. It's for sequential. You're doing subtraction, then you're doing multiplying by 2, or dividing by 2, or subtracting by 2, something like that. You're doing sequential matter. Single instruction, single data stream. Okay, speed is limited depending on the rate at which this information is transferred. That's SISD for you. SIMD is single instruction but multiple data stream, which means you have multiple data but you have a single instruction. So multiply all of them by 2 or by 4. They just multiply all of them by 4. So single instruction but for all of them. So it becomes 8, 8, 8, 8. Okay, like that. So single instruction but multiple data stream. Execute a single instruction on multiple data values simultaneously using many processors. Single control unit does the fetch and decoding for all processors. Widely used in 3D graphics and video games. You can say widely used in matrices. Multiply all of the elements in the matrix by 2 or divide by 2, something like that. Okay, so SIMD. Then we got MISD, which is not applicable. I mean, it's not very popular because you're executing different instruction on different process, but all of them operate on the same data set. It happening all so many instruction operate on a single data stream. Okay, so it's not a commonly used architecture. Execute different instruction on different process, but all of them operate on the same data set. MIMD is popular, literally popular. You can say it used in supercomputers. So using multiple processors, each one of them can take its instruction independently. Execute multiple instruction on multiple data set. When carry out parallel processing, process need to be able to communicate. The data which has been processed need to be transferred from one processor to another. It happens all the time. Okay, faster method for handling large volumes of independent data. So it can be used for those when we need to handle large volume of independent data. The data should not be dependent to one another. It must be independent. Any data which relies on the result of a previous operation, dependent data would not be suitable. It would not be suitable in parallel processing. Okay, so that was the for architecture. Now let's move on to parallel computer system. So there are two forms of parallel computer system. There are two form system. Either it is cluster computer, where you have number of computers networked together to form a cluster. They are networked together to form a cluster containing a SIMD processor. Each computer remains largely independent. Okay, so you can say it is cluster computers since they are large independent. Or you can have massively parallel computer. You can just call it supercomputers, linking together of a number of computers, effectively forming one brain having so many thousand of processor, okay, with several thousand processor. So you actually making a supercomputer. So you are creating a supercomputer right here, okay, solving increasing complex problem. Very complex problem. You can just solve them in 5 minutes, even though it could take more than a year. Using massively parallel computers, you can say supercomputers. Each processor will carry out part of the processing and communication between computers. Each processor will carry out its own part. Each processor will carry out the part of the processing, and communication between computers is achieved through interconnected data pathways. Okay, MIMD architecture can be implemented. And supercomputer is the name to represent this system. Okay, MIMD architecture has been used. Now finally we have completed this, and we are coming to virtual machines. Virtual machines is when you are creating a mini machine inside a machine, and you can just having another operating system inside that virtual machine. For example, you are on a computer, you are using Windows, but now you want to know whether you want to know whether the I mean whether for example, you're having your own Android mobile, but yeah, for example, you are owning a window, but you want to know but you want to use Android app as well, mobile phones, Android apps. So in order to use that, you need an emulator, you need a virtual machine. So this is your computer, and you are just create a virtual machine where you have installed Android OS. You have installed Android OS inside a machine. So basically you have launched a mobile phone, and there you can just test all Android apps. Okay, so that's virtual machine. This is Windows, which we are having. So Windows is our host OS, and Android OS is our guest OS. And the virtual machine, we can create multiple virtual machine 1 for Android, virtual machine 2 for running iOS app, virtual machine 3 for Linux. You can create various virtual machine, and the one which create these number of virtual machine is known as a hypervisor virtual machine software. Okay, so that's the difference. So emulation of an existing computer system, you're emulating it. Control the physical hardware, it's a host OS. Running on a virtual machine is a guest OS. Running on a virtual machine is a guest OS. Control the virtual machine hardware. Hypervisor, virtual machine software that creates and run virtual machines. Okay, running on a virtual machine is a guest OS. Running on a host OS, control the physical hardware. And a virtual machine runs the existing OS and oversees the hardware using the guest OS. Okay, so you got the hardware is controlled by the host OS, and then you got guest OS, which is communicating between these two. Okay, The guest OS has no awareness that it is on the alien machine, which means it doesn't know that it's in a virtual machine. It's launching as it having its own hardware mobile. I mean, its own hardware. Like if I launch Android OS, and it doesn't know that's on a virtual machine. It's it's in a fantasy. It doesn't know it yet. So it's playing like it's having its own mobile phone, like that. So the guest OS has no awareness that it is on an alien machine. Believe it is running on a compatible system. Emulation engine refers to as a hypervisor. This handles the virtual machine, the resources of CPU, memory, HDD, and other devices, and map them to the physical hardware of the host computer. Okay. What are the benefits? Guest OS can be used without impacting anything outside the virtual machine, which means you can just use a virtual machine. You don't need an actual hardware. Possible to run apps which are not compatible with a host computer. Like for example, Android apps on a window, it's not possible. Useful for testing a new OS or a new app. Testing new OS, okay, or new app. More than one different OS can be made available on the one computer system. Different OS, so many virtual machines. What are the limitations? Do not get the same performance. Obviously, you are halving the performance if you're creating one virtual machine and you are taking the hardware, the resources. You are taking a part of the RAM, memory, CPU, speed, so you do not get the same performance running as a goes a guest OS. Building an in-house virtual machine can be quite expensive for a large company. Okay, implementation will not offer the same level of performance. Yeah, definitely. Okay, so these are the limitations, these were the benefit, and this is the end of virtual machine. Congratulations. So this is the map. You got a hardware. It's been there's been negotiation. It's acting as a negotiation between the host OS, hardware, physical hardware, and virtual machine software. Then virtual machine creating two virtual machines, guest OS 1 and guest OS is having two applications being run, guest 2 having a different application. So virtual machine software ensuring each VM are protected from each other while running on the host computer. Okay, so this was the virtual machine. It's the end of it. So now we are coming to Boolean algebra and logic circuits. So a logic circuit can be half adder. Consists of two things: half adder and full adder. And full adder consists of two half adder. Okay, two half adder. Half adder. What is half adder? It's one of the simplest circuit that can be used for binary addition. It's known as a half adder. Circuit takes two input bits and output a sum and a carry. So you are doing addition, right? 0 1, add them up, you get sum. You just plus them, you get sum. But if you get both one, then you will get a carry. Sum, carry. Okay, sum can be represented as or, carry can be represented. Okay, so this is the truth table and this is the circuit. So you are using XOR to to represent sum and AND to represent a carry. Okay, so this is XOR, this is a sum, this is a carry, this is the half adder circuit design. Now you come to full adder. If you want to add more than 1 plus 1, we're going to need a full adder, and full adder is equal to 2 half adder, essential for the hardware implementation of an adder circuit capable of adding larger binary numbers. Okay, essential for the hardware implementation of an adder circuit. Circuit manufacturer prefer to use NAND or NOR gates. The circuit consisting only for NAND gates has the correct logic to produce a C, and the C output is likely choice for implementation. The NAND gate is more preferable. NOR and NAND gates, it's all okay. So this whole thing was about this. We will come to this later. First of all, let's see what full adder really is. So full adder is, you have a half adder in here, then you give a sum, you get a carry, you just put it here, then you get another half adder, you get the sum, and the carry is connected here, carry is connected here. You give it input and it comes here, and you got the carry and you got the sum. This is the full header. Okay, it's equal to half adder and all 8. This is the circuit diagram. So I have just replaced the circuit, then I have just put the circuit here. Half adder, everything is the same. Okay, so this is a full adder circuit diagram. This is the logic. This is the two. So if you add 1, then you will get 1, add another 1 plus 1, you get a carry. 1 plus 1, you get a carry. 1 plus 1, the carry. 1 plus 1 plus 1, you get both sum and a carry. This is how you try to make an addition. For example, you want to add 101 plus 011 and you want to make an addition. So 110 and 101 each will go okay, you get an input from here, each will come here and it will give a sum and carry, then sum and carry, and then sum and carry. At the end it will be neglected, or maybe not. So right for now, from the beginning, the carry input is going to be 0, then you get 0 and a sum, you get a carry, then you get a 0, you get a carry, you get a 0, then you get a carry, then you just count all of them, 1000, so it's 1000. Okay, the last carry generated will be ignored and regarded as overflow. Okay, could be neglected, but let's just say, let's just ignore this. Okay, right now it's been notified, it's been counted as one, it's been counted 1000, so it becomes 1000. Okay, from the beginning the carry input is going to be 0. Alright, now we are coming to this. We prefer using NAND or NOR gates. NAND has a correct logic to produce a CNC output, is likely to choose for implementation. So circuit constructed using NAND gate. So this XOR is constructed using NAND, having, this is the circuit, and AND is constructed using NAND, OR is constructed using NAND. So all you have to do is just memorize the way it's being made, and then you can just put it here, half adder and full adder, and after that you can just simplify things. Okay, because like you having these and this, there's been a duplication, so you just cancel them out, and you're also having these duplications, so just cancel them out. It cancels one after another, because for example 0, first of all the input is 0, 0 will be 1, and then it will come here, 1 would be 1, but then it would be 0. So same thing. That's why you just need to cancel them out, to simplify. So this is the whole this is the whole simplified circuit. Okay, and if you ever need to find out the circuit, then I guess you just need to use the truth table. For example, the truth table for this one is, for example, you got, or let's start with AND. You got AND, right? A, B, and then you just need to know AND. So if you give 1, okay, 0 0 1 1 0 1 0 1, and you want the output as 0 0 0 1. So how to convert this in NAND form? So if NAND means, so 0 0 would be 0, or you can just see here 0 0 is 0, but then it is NAND, so it will be 1 1 1 is 1, but then it will be converted to 0, so you get 0. Okay, 0 1, if you get 0 1 0 1 0, it would be 1, and then 1 1 is equals to 1, but it would be 0. Same thing here, 1 1 is equals to 1 0 0 0 is equals to 0 1, so you get 1. So you just need to use the truth table, or you can just memorize it. It's up to you. Okay, memorize it, and that's it, and then implement it, and voila, this is full circuit and half adder, full adder. Okay, then the next thing you got is the Boolean algebra. The Boolean algebra is used to represent circuits into algebra. Okay, so let's start from here. AND denoted as dot, or denote plus, not denote this, not denote this. The slash is known as not. Okay, NAND means having a dot b and then slash. NOR means a plus b and then slash. Okay, XOR means this. This symbol is known as XOR, while this is known as OR. Okay, then you got the set of rules. Then you might need to use it. The first one is commutative law addition. So if you got a plus b, then you can just write it down as b plus a. Addition and multiplication. A plus b is equal to b plus a dot b is equal to b d dot a. It's very easy. Very easy. Then you got associative law. We are doing addition and multiplication, so it's the same, it's not very difficult. A plus b plus c, if it is in bracket, then you can just write down in this way as well, and you can write down in this way as well. B plus a plus c, just give it different bracket to different elements. Same thing for multiplication, same thing for addition, associative law and commutative laws. Okay, they're very same. Then you have distributive law, where you are multiplying this. Okay, a is multiplying to b, a is multiplying to c, so you got a dot b. It's complete math. You can just see this. It's complete math. A is multiplied by b, so a dot b. A is multiplied by c, so a dot c. Distributive law is very easy. It's a complete math. Identity law is, yeah, it's a little bit tricky. We all know this one. It's complete math. If you multiply this by 1, then it will be 1. Okay, so both of them are complete math. It's complete math. Complete simple math. You can just remember so easily. So if any element is being multiplied by 1, it will be remain 1, and if element is being added by 0, it will remain a. Okay, yeah, so this is identity law. Then you got null law. Okay, this one is tricky, not this one. If any element is multiplied by 0, it will become 0. This one is tricky. If any element is added by 1, instead of 0, it will be itself, but if it is added by 1, then it will become 1. Okay, then you got independent law, where you can, if you have element a, then you can also write down as well, like in this way as well. Okay, and if you have these element be multiplied to one another having same element, then you can write it down as single a as well. So independent law is widely used in here. You need to understand this will help you in every question, because it is so much used. I will show you how I use this. It's very important. Okay, complementation law is when you are multiplying the element of its inverse, it will become 0. This is very easy. A plus a inverse is 1. Okay, this also makes some sense at some point. If you are adding the inverse of itself, then it will get 1. If you are multiplying the inverse of itself, then you get 0. Okay. Involution law is when you have two not, so these two are cancel out. That's why you get a single a. It's very makes sense. Absorption law is when, okay, this one, or no, it's not very tricky. Absorption law, right here you can see that you are taking a common of a. So you can just see this. I've done like this. You have taken the common of a, you get a plus b, and when you add it by a number, you will get a dot 1, and you get okay, you can just see this, that I've taken a common a. It's complete math. I've taken a common of a, and I got 1 plus b. 1 plus b is 1, so I've written down 1, and then a dot 1 is a. It's a complete math. That's why I got a. And as for here, okay, so a is multiplied by a is multiplied by c, then b is multiplied by a, b is multiplied by c. A is a, then you got ac, you got ab, and you got bc. You can take the common of a. Okay, let me do right here. you can take the common of A. So taking the common, you got 1 plus C, then you got A plus BC, and you got A, as we know it will happen like this. Then you got A plus B plus BC. You take the common of A, and you got 1 plus B plus BC. Again you will get A plus BC, and there you go, A plus BC, and there you go, A plus BC. You got this finally. So it's been completely proved. Then you got number 10, redundancy law. So redundancy law is very important. Okay. So redundancy law is it's been used when this one is a little bit tricky, and also I myself have found this very hard to remember, but there is a concept, there is a technique. If you get the inverse of this element, then you will get P. You can just imagine like this, that this element is pushing this element, this is his own inverse, and then you know eliminating this, and then you just get A plus B. Same thing vice versa, if you get the inverse and you got the element be multiplied by this element, you just cancel eliminating this, and you get A plus B inverse. Okay, it's a very interesting concept, but you just need to find a way to remember it. I've just told you how to remember this, but whenever you get the inverse of this, okay, you just inverse of one another, like B inverse, and you got B, so it will come A plus B. B, and you got inverse B, then you just get A plus B. You just count these A B, and you get, and then you just add them up. Okay, so this is redundancy law. The most important law is this one, redundancy law, and this one, very important. The rest are very simple math, very easy to remember, very easy to understand. Then you got finally the De Morgan's law. It's also very interesting, very important. Supposing if you got A dot B, or you got A plus B, and you got the not, so you just, if you try to break it down, then the sign will change inside. Okay, if you try to break it down, like you have this, like for example you have this, you can imagine this as having a block, and you just break it down to become in pieces, so the sign will change. Whenever you try to break it down, the sign will change when you break it down. Like you have this, okay, and if you just break it, the sign will change. Okay, so you got A dot B, you just break it down, the sign will change, A plus B. You got A plus B not, break it down, you got A dot B, sign will change. Same thing. This is De Morgan's law. This is also very important, and sometimes they ask you to prove it, or maybe not, but nevertheless it's very important rule. This is very important, this is very important, and these two are very important. Oh sorry, this one is very important, this one is very easy. So finally you got the Boolean algebra laws, and now let's see here. For example, you got the circuit, you just, and you, let's say you have this is not this NAND, so you got B dot C, having an and you put here the line representing a NAND gate. Okay, then you got A, and this is the NOT gate, this is the NOT gate. Okay, this is the NOT gate. So oh wait, this is not a NOT gate, this is actually an AND OR gate. This is the OR gate. This is NAND. Okay, this is NOR gate. So having a NAND gate, you represent this like this, having B dot C, and then you put a line in here representing a NAND gate, and then you got a NOR gate, which means you are adding it like A plus B dot C, and then you put a line over it. So this is how you write Boolean algebra. Now what you have to do, since you have write it down that this is the Boolean expansion, this is the Boolean Boolean expression of this circuit. This is a Boolean expression of this circuit, and now we're just going to simplify it. And that's why we have memorized these, just to simplify things. We have to simplify it, and you can just see here I have used De Morgan's law. It break it down, it just changes the sign, and okay, this will cancel out so it will be B dot C. So this is simplified circuit, and now the new circuit form, it's much more simpler than this one. So this is a simplified circuit. You got another example of having this, and now you simplify. This is the Boolean expression. You need to simplify this. Now you can see here, first of all, you're going to put out De Morgan's law, so it will be breaking down and like this. Then this would be simplified. Okay, this will also be simplified. Then you can see here that I think this is simplified enough, but you can move forward and you can just multiply further. So a is multiplied to this, complete math. Okay, you're multiplying this, you got this. A dot a would be a. Okay, b dot b would be 0, so whole thing would be 0. Got a dot b. This is a simplified circuit. Okay, and I don't know about this. Okay, I was proving this. Okay, yeah, I was proving this one. Okay, so this was the example. Then you got another circuit, and let's suppose you don't want to do the method, you don't want to simplify the circuit in this manner, like having the Boolean expression, and then you just try to make it simplify, simplify things by using these formulas. Instead of using this method, you have another one, which is by using a truth table to simplify things. So you're going to just have this circuit diagram, you're going to find out the truth table, and after finding the truth table, you're going to see which one has the output 1. You try to notify it, and then you're just going to see like a dot b dot c, but it is 0, so it will put slash over on their heads. You got 0 in a, 0 in c, so slash on these only, not b. B is 1. You got b c, so b c. A is above is slash because it is 0. Same thing, and then you're going to add all of them, and then you're going to simplify them. Okay, then you're going to simplify them. So again, you're going to use the same logics, the same rules applying in here. Now okay, whenever you got these kind of question, and you will definitely going to get these kind of question, literally I'm telling you, because I know the paper, it will obviously, it always come like this, always this very it looks completely ridiculous. Seeing this will give you a heart attack or something like that. So let me help you. Okay, right, for now let's suppose, first of all, you need to see the common. That's number 1 for you. Right here in front of me, I can see that the common is you are having BC. Okay, you're having BC. These two are common, and now you can see here that AC also common. Okay, and these two are quite different. So these two are at some point very common to this. So you're going to use the independent law. That's why I was telling you that independent law is very important. You are going to use independent law because you can see right in front of you that this one can be applied to this, it can be applied to this, and it can be applied to this because it has more common. That's why you need more than one. You need two. You need at least two. So according to independent law, when you have a, then you can also write down as a plus a or a dot a, etc. You can do that. So I've done it right like that. So I got another ABC, and now I'm going to use this to apply in here, use this to apply in here. Okay, I have taken a common. You can see here it will become 1. It will become 1. It will vanish. It will become 1. It will vanish. Okay, you got I've simplified things, and now I'm going to take another common. A is common to in here, or no? Okay, both of them have okay, not even that. Let's see here. So if I take the common of A, okay, I can use this for here, and for BC I can use this for here. Just C common, and you got the inverse of B. For B you got the inverse of C for C. So I'm going to use it here. Wait a minute. Okay, I'm going to use this here. So again, going through this, got in this way, and in here I can also okay. Now you can see you can use the redundancy law, since you have the inverse and you got this. So this will be gone, and then you'll get B plus C inverse. I'm using the redundancy law. Okay, redundancy law is being used. Redundancy law used. Okay, and then I'm going to simplify it, and then I'll take the common of okay. So I can take the common of I can take the common of C here, and then A inverse and A, it will be sorted out by, it will be used by the redundancy law. I can use for this one or not. Okay, let's see. Okay, just simplified, you get 1. Okay, and then you can take a common of here, and then you get 1, and then you got simplified circuit answer. Okay, so this is how you try to use the Boolean expression. This is how you try to simplify things. There are two ways to do this. Either you will use a logic circuit. They will give you a logic circuit, and then you're just going to find out that which one of the output is 1, and then you just add all of them, and then you try to simplify them. Or you got the circuit, and then you need to find this Boolean expression, and then you try to simplify this. You just simplify this. Okay, so there are two ways, and let's move on. Okay, so now you have so many questions. Let's see here. It's the same thing, literally same thing. I'm going to take the common of C, yeah, or okay, yeah. So I have taken the common of, I take the common C, and I got A dot C. Okay, how did I got this? So if I got like C dot, and I got A plus A dot, or wait, I can take another common. Okay, so I have taken A dot C. I have taken the common. Okay, this one is common, this one is common, and I got B plus B naught. It will become 1, so you got A dot C. Okay, it's very simple. Then I take the common of A, and I will get C, and yeah, I have just used redundancy law, okay, in here, and I've just got this, and there you go, voila, this is the answer. Okay, I have used redundancy law in here. Redundancy law has been applied. Redundancy law. Okay, move on. Let's move on. Okay, I've this is the same thing as here. Same thing, literally the same thing. Either they give you a circuit, and then you got a truth table, and then you just try to find them out, or they will just give you a simple question like this, that use the Boolean algebra to simplify this expression. Use the Boolean algebra to simplify the expression. There are three ways that they're going to give it to you. They're going to give it to the circuit, and then you will just find this Boolean expression, then you simplify it. Then, or they will give you the truth table. You just find them all of this and add them up, and then you simplify it. Or they will give you just simple question, and then they will ask you to simplify this Boolean algebra, simplify this expression. Okay, so there are three ways that they were going to throw the question at you. So the same thing here, you got this question, and you can first of all you're going to find out which one of them are common. So ABC can be applied in here, and can be applied in here because these three are common. Again, can be applied in here as well. So you can have at least two more. So I'm going to use the independent law. I got two more. So all of them are 3. You just keep on simplifying them, the same thing, and you got the answer finally. So that's the answer. Or maybe not. You can again simplify it. You can take the common of A, and but still it's the answer, you can say. It's a complete at some point. Let's see. Let's suppose, okay, let me just take a common. If I take a common, I will get B naught and I'll get C and D. Okay, now this is the answer. Okay, so this was the Boolean. Now, okay, now we are coming to Karnaugh map. After completing the Boolean algebra part, we have come to Karnaugh map, and Karnaugh map has been used for reducing expression, the same thing as doing using Boolean algebra, using these laws to simplifying these things, simplify them. But it could be possible that the question that we've been asked, that simplify this, could took us a very long time. It took us quite a time and quite an effort that we are putting it into making it simplify and get the simplified circuit. Instead, we're going to use the graphical method, and this is very effective. The graphical method of Boolean logic expression reduction. So Boolean expression can be reduced to its simplest form. Not only it will reduce it into simplest form, but also it will make sure that it will be reduced in a much faster way as much as possible using graphical method. Okay, so number of cells in a Karnaugh map is equal to the total number of possible input variable combination. If for example you got two inputs A, B, then you will get a square box. If you get three inputs, then you will get the input like this, rectangular. Okay, if you get four inputs, then you will get a big box like this one. You get big box like this. Okay, if you get two input, you will get this box. If you get three input, you will get this box. If you get four inputs, you will get this box. And we will discuss what it means. For now, let's move on. For example, first thing, this how it works, how this Karnaugh map works is that you will be given a truth table. Okay, you will be given a truth table, and then you're just going to do the same thing as we have done in here. You're just going to take out these, which one is output 1, you just take them out, and then you're just going to put them, instead of adding them up, instead of adding them, you are going to put them in a graph. Okay, so you got three input, which means you're going to use this box right here. So you got three, you're going to use this box. Okay, so A, B, C. If you got two input, then you write down as in this way, A, B, and then so you got this box 0 0. It could A, B could be 0 0, or it could be 0 1, it could be 1 1, or it could be 1 0. C could be 0 or 1. So 0 0 0, which one is 0 0 0? This one is 0 0 0. It was 1, so you put 1. Then 0 1 0. This is 0 1 0. Then you're going to put 1. Okay, like that. So AB is 1 1, and C is 0 1 1 0. 1 1 0 is this 1. So you're going to put 1. After putting them, then you're going to group them. After making a graph, you will group them. Okay, how to group them, let me show you. So you're going to group them in this, either you can group them in 2, 4, or 8. You cannot group them in odd numbers or in odd form, like having 3 ones. So instead of grouping them like this, you're going to group them like this, two groups and then another 2, and the groups can be overlap. Okay, so you got 2 groups. Same thing here. I got 4, so I'll just group them 4. Now group them right here. So I got 2 different groups. Now I'll just simplify them, writing them down, and then I'm going to see the letters in each column must be same, otherwise cancel out. These are all not same. This will be cancelled out. This will be cancelled out, since these are not same. This one is same, so it will be taken out. Same thing here, and then you're just going to add them, and this is the answer. This is a simplified circuit. Okay, so this is how you take out. Okay, you put them in a group, you put them in this graphical form, and then you just group them, and separately you just simplify them. You see that the letters in each column must be same, otherwise they will be cancelled out. So the C naught is same in all of these, but these two are at some point different. Like these two are same, but these two are different. All of them must be same, otherwise it will be cancelled out. So they are cancelled out, and finally you got C naught. Okay, then after finishing, then you're just going to add them up, and then you got the simplified circuit. Same thing has happened here. For example, you got two inputs, and you might be given a circuit or something, but I have just written it down directly and just to show you. It's nothing more than just an example. Otherwise you will be given the truth table, don't worry about it. Right now I'm just giving an example that you have been given this graph, and then you need to group this. So I'm going to group in this way and this way. I'm going to separate them, simplify them, and I'm going to add them, and this is the answer. This is the simplified circuit. Okay, same thing here. Like you have four inputs, you have this whole thing. Okay, so there are different ways to group them. Either you can just do it separately, like two here, two here, two here, and then you just simplify them, you get the answer like right here. Or you can just do here, and this is a special way of grouping them. Like if we have 1 1 in here, and if you go from you got 1 1 here and got 1 1 here, and supposing that if you go on this side and you come back here, then you can just group them like that. So you got 4 and you got 2. Okay, this is another way of grouping them. Otherwise you can do in this way as well. They will both give the same exact answer, so don't worry about it. Okay, in here, just an example, just to show you how many ways that can be grouped. Supposing you have got 4 1s, so you can just group them like this, or you can just break them down like grouping them like this and this. Okay, you can group them like this, or you can group all of them in one go. Okay, 1 2 4 in sequence. You got 1 in each corner, so you can just group them like this, like 1 1. I mean, yeah, like you're grouping them, they're in each corner. So grouping them like this, you get one group. Then grouping them like this, you got another group. Okay, then you just simplify it, and voila. Okay, there's a difference. Okay, either you can just group them like this, you got 4 in one group, or you can just do it like this. You can do in this way as well. Okay, yeah, similarly you got 4 1s, so you can just group them like this, or you can just group them like this as well. You got 4 like that. Okay, like this. We can have 4 groups, or you can just have one group taking them all at once. Yeah, this another group. Same thing here. You got 3. You have like this 1 1 1 and 1. Group them, then group another one, and then group another one, and the groups can overlap. Okay, and the groups must be in the power of 2. 1 2 4 8. Can be 1. It cannot be 1. It can either be 2 4 8 16 like that. You can just group in this way, okay. So this was Karnaugh Map. Very very easy graphical method to simplify the Boolean expression. That was Karnaugh Map. Finally, now we are coming to flip-flop. Flip-flop is used for making memory, for storing memory. For example, a flip-flop can store either 1 or 0 flip-flop. There are two types of flip-flop, either SR flip-flop or JK flip-flop. Okay, let's start with SR flip-flop. Memory can be created memory can be created from flip-flop. It's a 1-bit memory, hold a single bit. Okay, for now we are talking about the SR flip-flop. Okay, or we are talking about the flip-flop overall for now. So it's a 1-bit memory, it holds a single bit, it reads a bit that was saved, and it can also change the value as well, set the bit to 1 or reset or clear the bit to 0. So there are two types of flip-flop. The first one is SR flip-flop, considered as one of the most basic sequential logic circuit possible. 1 bit memory bistable device, it's for 1 bit. There are two inputs, either you can just set or you can do reset. That's why it's known as SR flip-flop. SR flip-flop. Okay, set reset flip-flop. Constructed with two NAND gates or two NOR gates. Active low input respond to respond to active high inputs. Different categories. You can do it either in one, but having different purpose for doing this. Okay. Then you got, these are known as output and they are a complement of each other. So this is the circuit, this is the NOR gate, and this is the NAND gate. Okay. So you can just see here that how they are connected to one another. So these are inputs, these are output, and they are complement to one another. Must be complement. They must be complement. Must be complement of one another. Okay. So right now, first you try to initialize it. You get a value initially. So you got 1 0 1 0. If you're getting 1 from here, and you might get a 0. Okay, right now you just set 1 and 0 here, right? Okay, so the output from here, it's 0, it's coming here. So 0 0, it become this is NOR gate, right? 0 0 is 0, but then it will be 1, so it becomes 1. 1 is coming here, 1 1 is 1, but then it will be 0 because it is NOR gate. Okay, so this is how you create this SR gate. So this is the NOR gate. You got this two table for it. Okay, initially it was this, but if you, okay, initially it was this, but let's suppose you are putting S0, the output didn't change, so you are just setting it. This is known as set state. But then if you put 1 in here, right, for right now it was 0, both of them was 0, but if you put 1 here, then it will be reset, because 1 will be gone to 0, this will be become 1, so you can say reset. Then if you try to put this 0, then the output didn't change. So there are two state. This one is known as the set state, this one is known as the reset state. Okay, and if you get both 1 at the same time, and it will be 0, which means it is undefined, and this is something that we need to prevent it happening. This is something that we need to avoid. Okay, we cannot have both 1 at the same time, otherwise it will give an undefined output. Same thing happening is in NAND gate as well. There's a different, you can see that there's different truth table. That right in here you're putting 0, so it didn't change. In here you're putting 1, it didn't change. Okay, you can see here R, you can see here S. Okay, if you put 1, it didn't change, so it's known as a set. But if you put a 0 after making them 1 1, you put this one 0, then it will change. You can see the output, this will become 0, this will become 1. Then if you put 1, the output didn't change. So this is a set state, this is a reset state. This is how you are saving 1 bit memory. Okay, and if you get both 0, then it will be both 1, and then this is also known as undefined range, undefined output. Okay, so this was the SR gate. Okay, now so we are coming to JK flip-flop. Okay, so it's an improvement of the SR flip-flop, because it prevents any undetermined output. You won't get any kind of undefined output like this. So, and yeah, it also has a clock pulse to synchronize input. Okay, so you have this was a SR SR flip-flop, but now what we are doing here is we are adding this and this NAND gate, another NAND gate, and we are connected in here, connected in here, and we got the clock. Okay, this is the truth table. You can just see here the similarity, because you just take this and just put it in here. The only difference here is you just take another, this is a NAND. You have put this wire connected to here, put this wire connected to here. You got J, you got K, and you got the clock connected to here. and there you go, you got the JK flip-flop. Okay, this is the truth table. Supposing you have the initial values 0 0 and 1, you got the initial values this, final values this. Okay, it didn't change. If you have in this way, if you have the initial values this, and yeah, then it didn't change, it remained the same, so retain same. But if you put 1 in here and 1 in here, then it will change. Okay, and if you again after changing it, if it still remain the same, then it will not change, it will just this is the reset part, because now you can see it just, you know, it's changing, but then after that it remained the same. Then if you put 1 in here, 0 in here, then it will change here. You can just see here, it will change right here, it's changing right in here. Yeah, so you put 1 in here, 1 in here, it will change, and it will, if it remain the same, then it will not change. This is reset. Then if you put 1 in here and then 0 in here, then it will not change, but after that it will change. This set. Okay, but if you put all of them 1, then it will change, it will toggle. Now the clock cycle is preventing this to have undefined output, so it's just changing the values, and again the same thing comes, then it will again change the values. So this is retain, same thing happening. This is reset. If you put 1 in here and it will, you know, remain the same, then it will change in here. If you put 1 in here and it remains the same, it will change in here. And if you put all of them 1, then it will just toggle, changing values. Okay, and another thing you need to understand about the JK flip-flop is, like, for example, you have the initial value 0 0 and clock is 1. You got the initial values of this, you have put 1 and 0, and it doesn't matter, it will remain the same, since, you know, it doesn't change whether it's 1 in here or 1 in here, it will remain the same. Okay, so there's no retain, same. Supposing you have k is 1 and clock is 1, this is 0, then now you can see here, if q, the value of q is 1, then it will change to 0. Okay, and if the q slash is 0, it will change to 1. In this format, it must be in this format. So right now it is in this format, so it will not change. So this is known as reset. Okay, so you are resetting it. In here you have put j is 1 and this 0 and this 1. So if, for example, if you have 1 in here, slash 1 is slash q is 1, and you got 0 in here, then it will be changed to 0 and it will be changed to 1, which means it must be in this format at all cost. So now you can see here, this is set, this is reset. If it is in this format, it will be changed. I mean, it must be in this format, 0 and 1. It must be in this format, otherwise it will not change. Okay, I mean, it must be in this format and it will not change. If it is in this format, if the value of q is 1, then it will change to 0. This is set. But if the value of q is 1 in here, then it will be changed. If it is in this format, then it will not change. Okay, otherwise it will not change. And in here right now you can see here that if you put 1 1 1, and you know, the values will just change. If the value of q was 1, if the value of q was 1, then it will become 0, and if the value of q was 0, then it will become 1. That this is the meaning of toggle, because you're changing it every time. Okay, so topic hardware. Thank you so much for watching, and I'll see you in the next video in the next chapter, system software.